Jason.
Thank you for the introduction and the invitation to speak, and thank you all for coming here today. This is ongoing work with Griffin Johnston from Emory. He's a grad student at Emory University. So I'm excited to give an Iowa State exclusive into this work. It should be on archive in the next month or so, but this is an early preview. So I'm going to be talking about oddtown and eventown problems. So I'll give a bit of an introduction into those problems, and then I'll talk about the new problems. Okay, so before I do that, just want to establish some notation. So we're going to be talking about subsets of an n element set, and most of the time we're going to use brackets n, and that will be the positive integers 1 up to n. And when we talk about these subsets, we're going to use the following notation. So the power set is going to be 2 to a. So this is all subsets of your given set A. And then we'll also use the notation A choose K to be all size K subsets of your given set A. And so we use this notation because there are exactly 2 to the cardinality of A such subsets of your set A, and cardinality of A choose K, subsets of size K of your subset A. The other piece of notation we're going to use is the characteristic vector of your subset A. And so what this is it's a 0, 1 vector. You can think of it as being an F2 to the n, where the jth coordinate is going to be 1 if and only if the element j is in the underlying set A. So this allows us to perfectly encode subsets of an n element set as vectors. And more importantly, we can then use the structure from linear algebra to prove facts about the subsets of an n element set. So if you've seen this before, probably the first thing you saw was the oddtown theorem. And the oddtown theorem looks at subsets of an n element set where each subset A in your collection has an odd number of elements. And between any 2 sets in the collection, there are an even number of elements between them. So throughout today's talk, we're going to give conditions on the sets, the pairwise intersections, and other things. And then our question is, how large of a set family can we have? So the oddtown theorem says, if the sets have an odd number of elements and pairwise intersections have an even number of elements, then the most number of sets you could possibly have is the size of the ground set n. So this is one of the first theorems that uses this linear algebra method. And the proof is nice and short, and you can fit it on one slide. So let's go through that proof. So what do? We start off with an arbitrary collection of m sets where they satisfy oddtown rules. So each set has an odd number of elements, and then pairwise intersections are going to have an even number of elements. So what do? You then encode each of the m sets as its characteristic vector in F2 to the n. And one of the nice things about F2 to the n is the inner product is going to tell you something about the sizes of the sets. So if I take a characteristic vector of one of our sets, A sub I, and I take the inner product with itself, what I'm doing is I'm summing over all the coordinates, and I'm only going to get a 1 in the event that the corresponding element is in the subset. So the inner product is going to spit out the size of the set mod 2. And since this was an oddtown family, we're going to get 1 when the indices agree. When the indices don't agree, what the inner product is going to give us is it's going to give us a 1 each time there is an element that's in both subsets. So as I sum over all the coordinates, I'm going to get the size of the intersection, which is going to be 0 mod 2. And so what this allows us to do is it allows us to state this sort of diagonal condition where the inner products are only going to be 1 on the diagonal, or when the indices agree. And then using either sort of Graham matrices or just the definition of linear independence, you can show that these M vectors are linearly independent. And what that means is you have M vectors that are linearly independent in an n-dimensional vector space. So therefore, the number of vectors is at most the size of the number of vectors is most the dimension of the vector space, which is n. So this shows a upper bound of n for odd-town families. And you might wonder, can you actually construct things that have n elements? And it turns out there are many ways to do so. The first way, probably the first thing that comes to mind, is to take the singletons. So the singletons, each set is going to have size 1, which is odd, and then pairwise intersections are going to be 0. But that's not the only thing you can do. You can also take vertex disjoint cliques of odd uniformity. So I can partition my ground set into sets of size k plus 1. And on each set, I'm going to take all size k subsets. So this requires some divisibility condition on n. But if I have that condition, then if I take 2 sets from the same clique, they're going to have k minus 1 elements in common. And here k is odd. So 2 sets in the same clique are going to have k minus 1 elements in common. So k minus 1 is even. So that is the desired pairwise intersection condition. And if I take 2 sets from different cliques, since we partitioned the ground set, they're going to have no elements in common. So this new family A2 is going to satisfy the pairwise intersection even condition. And each set is actually going to have k elements. So the sets have odd size. And provided n satisfies that divisibility condition, you're going to have exactly n sets in this new family A2. And there are a few other things you can do. You can take a large sunflower and throw in a couple of sets to get another construction that has n sets that satisfies odd-town rules. So there are many extremal odd-town families. And more can be said about that. So here's odd-town. Oh,
I think we have a question here.
okay,
Sorry,
yeah.
It's from the previous slide. I was thinking about it. Can you go back? This inner product, when you get a copy, it's just the normal dot product, right?
Yes, it's the normal dot product, but everything is in F2 to the n.
So when you get a 1 for every time you have an overlap between a sub I and a sub j?
Exactly. But you would get an even number of 1s.
Oh, I see. I see. Okay. All right. Thank you.
Yeah. And then you get an odd number when they are the same set or the same vector. Yeah.
Thank you.
Yeah. Okay, so that is oddtown. And oddtown says the sets have an odd number of elements and pairwise intersections have an even number of elements. So there's also the problem where when you sort of reverse those conditions. This is sometimes called dual oddtown. So in dual oddtown, the sets will have an even number of elements, and the pairwise intersections have an odd number of elements. This is sometimes called reverse oddtown, but I like dual oddtown because it's very closely related to the oddtown we just talked about. If I take a dual oddtown family and I take an extra auxiliary element, let's just say n plus 1, and I throw in n plus 1 to every set, that's going to change the cardinality of my sets from being even to odd. And then the sizes of the pairwise intersections, well, since that special n+1 elements in both, the pairwise intersections are going to go from odd to even. So what this does is it takes a dual oddtown family and turns it into an oddtown family. And I can do the same thing with n+2 and get it back into a dual oddtown family. So what this suggests is the largest such dual oddtown family should look pretty similar to the largest such oddtown family. And that is indeed the case. So you can show actually a similar proof that if you have a dual oddtown family, the largest such you can do is going to be n-1 when n is even and n when n is odd. So it's very similar to the classical oddtown where the answer is n. Okay, so that's oddtown. It's a nice story. In the talk, we talked about eventown, and that's also a very nice story. Rebecca Stead said it is beautiful, mysterious, and deeply satisfying. I think she was referring to this children's book here. But the eventown that we care about with set systems, I would argue, is also beautiful, mysterious, and deeply satisfying. So let's take a look at it. So in eventown, the sets have an even number of elements. And then the pairwise intersections also have an even number of elements. So I have two similar conditions to both the oddtown and the dual oddtown problem. And if you're seeing this for the first time, you might think, oh, the answer should be similar. It should be something like n. And it's actually a bit surprising that the answer is much, much larger than n. In fact, it looks more like 2 to the n over 2. So if you have a collection of subsets that satisfies these two properties, then you're no larger than 2 to the n over 2. And in fact, this is actually possible to achieve. So that is best possible. So let's talk a bit about the construction. So in the construction, I'm just going to assume for this slide that n is even. And what we're going to do is we're going to partition the ground set into blocks of size 2. So we have these blocks. You can see them in blue below. Each of them has 2 elements. It may be convenient to think of this as each element in your ground set, you pair it up with a buddy. And then we take all possible disjoint unions of the buddy pairs. Okay, so it's kind of a mouthful to say, but what we get is we get this family B that's going to be all such unions. And as you can see, there are 2 to the power of k such unions. And here k is equal to n over 2. So if this family satisfies eventown rules, this would be best possible according to the previous slide and the theorem there. So let's see why it satisfies eventown rules. So I need to check that each set has an even number of elements. So I look at all the sets in B, and each set is going to be a disjoint union of these sets of size 2. So each time I'm going to be adding up 2, and therefore I get an even number. The pairwise intersections also have to be even, and it's maybe a bit more subtle, but the pairwise intersections are also going to be a disjoint union of sets of size 2. And the way to think about it is I'm taking a disjoint union of all buddy pairs that are in both groups. So maybe the first and last pair of buddies is in both of the groups that they come from. And even if I have an odd number of buddy pairs, I'm still going to have an even number of total people or total elements. Okay, so that is eventown. And to prove that that is best possible, you can do something similar with characteristic vectors. it just becomes a bit more subtle because all inner products are going to become zero. And you end up with something that's called a totally isotropic subspace. And you can prove bounds about totally isotropic subspaces and their dimension. And that ends up giving you the 2 to the n/2 bound. Okay, so that is eventown. You might wonder, what about dual eventown? So in dual eventown, here all sets are going to have an odd number of elements, and all pairwise intersections are also going to have an odd number of elements. And why we call it dual eventown is I can take an eventown construction, like the one on the previous slide, and I can add an auxiliary element. You can think of it like n+1 to each set, and that is going to cause each set to have an odd number of elements and each pairwise intersection to still have an odd number of elements. So this is something that I'm not entirely sure if it's in the literature. So we are including it in the appendix, but it turns out the best you can do is essentially the same, but now instead of n/2, it's n-1/2. So it's similar, but you do have to do some a little bit more care in terms of proving that upper bound. Okay, so this is oddtown, dual oddtown, eventown, dual eventown. Many of it has been studied for, has been in the literature for a while now. One of the reasons we got into this project was the breakthrough of Conlon and Ferber. And what they did is they used those sort of 4 problems to improve, and some randomness and a nice argument to improve upon some of the bounds on multicolor Ramsey numbers. So I was on a run one day, and I was like, I wonder if you can sort of extend what they did to hypergraph multicolored Ramsey numbers. And I sort of came up with this problem. The long of it is, it turns out the stuff that we're going to do in this talk give good bounds. But that is how I initially came about thinking about these sorts of problems. So what are the new problems that I thought about during the run that I had hoped would have implications for multicolor hypergraph Ramsey, which is a mouthful to say. So the new problem is given a vector. So this is a vector in f2 to the k, and it's really just to sort of keep track of what problem you're thinking of. So someone gives you some vector, and now a set family is going to satisfy that vector's intersection pattern if, when I look at the ith coordinate, it's alpha sub I, that means all I-wise intersections are going to have size alpha sub I mod 2. So we have a new collection of problems where someone tells us what intersection sizes the different number of distinct sets must satisfy. And then we try to come up with the largest such set family that's going to satisfy those intersection properties. So sort of a lot to unpack. The vector here is just sort of keeping track of what problem we're doing. So to sort of summarize, one vector you could think of is 1, 0. And what this vector says is the set sizes are going to have size 1 mod 2. So the set sizes are odd, and the pairwise intersections are going to have size 0 mod 2. And so that's going to be the classical oddtown problem. The other vector you could think about is 0, 0. And that says the sets themselves have an even number, or 0 mod 2 elements, and the pairwise intersections have also an even number. So that is the eventown problem. And you can kind of see where this is coming. there is the dual odd town, which is going to be this vector, and the dual even town, which is the vector 1, 0. Okay. And with this formulation, you can see the connection between a vector and its dual. Namely, they differ by the all ones vector. So if I look at odd town and dual odd town, the difference between them is the all ones vector. And that makes some sense. Adding an auxiliary element is just going to flip all the sizes of the intersections. And same thing with eventown and dual eventown. They differ by the all ones vector. Okay, so that is just the framework that we are going to look at today. Let's see a truly new problem. So we're looking at alpha is 1, 1, 0. And so a set family is going to satisfy that intersection pattern if the sizes of the set are 1 mod 2, that's that condition there. The pairwise intersections are also 1 mod 2. And now the 3-wise intersections are going to have size 0 mod 2. So this is a new problem. But if I look at just the first two conditions, I say all sets have size 1 mod 2, and all pairwise intersections have size 1 mod 2. So just ignoring that third bullet point, this is the reverse eventown problem, where the answer is 2 to the n over 2. Ignore the floors and -1s. It's something exponential. So the question is, by imposing this third condition, what's the answer now? We're now imposing more. And that is sort of what we'll explore today. By adding that new condition, how does the answer for the largest such set family change? Okay. So the next slide is going to have a lot of information, but it's going to include the answer to all 8 problems that you can ask by looking at the 8 possible vectors. Okay, so I'm going to take a deep breath too. A lot of information on this slide. Let's start with the first row here. The first row, when I look at that vector, I know any such family is going to satisfy odd-town rules because the sets have to have an odd number of elements, and the pairwise intersections also have to have an even number of elements. So what this says is, if I impose this additional condition on the 3-wise intersections being even, we don't lose anything. Maybe in other words, the canonical construction where you take all the singletons is still going to satisfy this intersection pattern. So the singletons are going to satisfy this intersection pattern because the 3-wise intersection of any singleton of singletons is going to be 0. If I look at this row here, it starts off with the sets having even size and the pairwise intersections having odd size. So that is, okay, it's hard to keep track of all these problems, but that is dual odd town. So it's the odd town, but you've sort of flipped it. And there the answer was either n or n-1. But by imposing this third condition, we're actually now the largest such thing we can get is n-1. So not a huge improvement, but it does rule out some of the constructions of size n that satisfy dual odd town. Actually, I think the constructions there are probably only projective planes. So projective plane won't satisfy that type of intersection pattern because we have no way to guarantee anything about the three wise intersections in a projective plane. They could have 0 elements or they could have 1 element. Okay. Looking at the second row, we see the eventown bound. So the construction with all the pairs of buddies, that construction, the three wise intersections are still going to be even. And here is sort of the dual eventown. So by adding an auxiliary element, the three wise intersections in those guys are still going to be odd. So not much is new on the second row. The fourth row is where things start to get new. So if I satisfy these first conditions, that means we're dual at eventown. So if I satisfy sets and pairwise intersections are 1 mod 2, we are dual eventown. However, by imposing this third condition, I now have a substantially smaller largest such family. So the largest such family looks more like n over 2, as opposed to over here where it's 2 to the n over 2. Okay. So what I want to do is talk about this third row and the fourth row. So the third row, we're calling it alternating oddtown because the vector alternates from 1s to 0s back to 1s and 0 to 1 back to 0. And in alternating oddtown, the answer is pretty close to n. So let's see why. So just repeating what was on the oversized previous slide, the answer here is either n minus 1 or n. For the largest such family, that's going to satisfy that intersection pattern. Okay, so let's see an upper bound. So we're going to start with an arbitrary such family that's going to satisfy the intersection pattern we care about. And now what I'm going to do is I'm going to take a set in this collection, and I'm going to consider all intersections from the family with that set. So given a set, I'm going to find a new family, f prime, that's going to consist of all the intersections with my given set A and some new f from the original family. So this will create a new family, and each set in this new family is going to have an even number of elements. So in this new family, all sets are going to be pairwise intersections from the old family, and therefore have an even number of elements. However, if I take 2 sets from the new family, it's going to look like A intersect F1, and I intersect that with A intersect F2. And so collectively, that will be a 3-wise intersection. So pairwise intersections from F correspond to pairwise intersections from the new family F prime correspond to some 3-wise intersections from the original family. And therefore, the pairwise intersections from F are going to have an odd number of elements. So this new F prime is going to satisfy the 0, 1 intersection pattern, which is the dual oddtown talked about. And if you remember, dual oddtown, the answer was either the ground set or the ground set minus 1. So one way which we get sort of improvement here is the ground set now is the size of the set A. So what does that mean? That means that if I have a very small set, we can't be very large. If I'm going to satisfy alternating oddtown, I can't have small sets, because then you can create a dual eventown with not too many elements. So what that tells us is if we want to construct a good alternating odd town, the sets have to be large. And that is exhibited in these constructions. So what do? I take either all n-1 size subsets of the ground set. So I need my sets to have a odd number of elements. So depending on if n's even or odd, we do one of these two different constructions. And the key is anytime I take a pairwise intersect or an intersection here, if it's distinct, I'm going to be throwing away a unique set, a unique element each time. So when I take an intersection from there, the sizes are going to be n-2, because each set here misses out exactly one element. And you can check that these two actually have the size in the claim up here. Okay, so that is alternating odd town, which was the third row on the previous slide. So let me just go back. So that's this third row here. And then the other one is similar. And now we're going to look at this fourth row problem. Okay, so the construction here, I call it a tale of two cities. So what we're going to have is we're going to have the first city be the elements from 1 up to 2k plus 1. And the second city is going to be the elements 2k plus 2 all the way up to 4k plus 2. And what we're going to do is our first set is just going to have that whole second city. So the first set just consists of the second city. And then the other sets, what do? They take all but one element of the first city, and then they take a unique special element from the second city. So each of these asymptotically is going to have a unique special guy in the second city. Okay, so this is a collection of 2k plus 2 sets when the ground set is 4k plus 2, so roughly n over 2. So let's check that it satisfies these intersection patterns. Okay, so first I take a look at my second city. The second city is going to have exactly 2k plus 1 elements, which is odd. So that one is good. And now if I look at the other a sub i's, they have 2k elements from the first city and exactly one element from the second city. So the first condition on just the sizes of sizes of the sets themselves is satisfied. And now if I take my set A naught and exactly one set A sub I, the intersection is only going to be the unique element from the second city. So in particular, the size is going to be 1. And if I were to take A naught together with 2 guys there, the size of that intersection is going to be 0. So if I take an intersection with A naught, both of those conditions are going to be satisfied. Okay. If I take 2 sets of these a sub i's, they're going to have no contribution from the second city because each set is going to have a unique guy in the second city. However, when I look at the first city, there are going to be exactly 2 elements that are missing. So the sizes of those intersections is going to be 2k minus 1, which is also odd. And similarly, if I look at the 3 y's intersections, that will be missing 3 elements from the first city, which will be even. Okay, so this is a construction, and what the construction suggests is if I have such a family, all the sets are going to have size roughly the ground set over 2. And this is sort of exhibited in the proof of the upper bound. So to prove the upper bound, we're going to prove 2 lemmas. So the first I call the sets cannot be too small lemma. So I start off with an arbitrary family that's going to satisfy that intersection pattern. And then what I can do is I can take any element at any set in the family, and I can do the same thing I did before, where I take all pairwise intersections with that, all pairwise intersections with the special set from the family, and that's going to satisfy a 1-0 intersection pattern, which is the classical oddtown. So that says the new family with that number of sets is at most the size of the ground set, which is now my special set F. The sets cannot be too small comes from if I have a set that looks like n over 3 in size, then my family can be at most n over 3. So that says that if a set is very small, then we already get a very good upper bound. Similarly, there is sets cannot be too large lemma, and this one's a bit more technical. I mean, you just have to be somewhat careful with defining sets and their complements. But it's a very similar idea where you look at a given set and you consider sort of pairwise intersections of now the complements. And you get some similar bound, which now says the number of elements in the family, -1, is at most the size of the complement of a given set. And so this says if I have a very, very large set, its complement's small, and therefore the number of elements in the family is small. So what can I do? I can take the 2 lemmas together, and I can add the inequalities. And what I'm going to get when I add the right-hand side is just the ground set n. But when I add the left-hand side, I'm going to get 2 times the size of family -2. So when I bring things over, I get roughly the size of the family is at most n over 2, which is essentially what the construction gives. Okay, there's some cases modulo 4, but roughly speaking, it's n over 2. Okay, so that is that 4th row. Now you can ask the same thing, but now with 4 y's intersections. So in this table here, I could include 16 new problems, but I'm actually just going to save some space and just include one of them with the understanding that the dual is going to be similar. So I look here, the one that we just talked about, the tale of 2 cities construction, it turns out that those 4 y's intersections are also going to be 0 mod 2. So that's the one that we just talked about. And now we have sort of 4 new problems down here. And all of those end up looking like the square root or 2 times the square root of 2 times n. Okay, so let's take a look at one of them. So this is the 1, 1, 1, 0, 0. So if I just look at the first 2 conditions, that's going to be reverse eventown, and the answer could be like something like 2 over n over 2. As I introduced that 3rd condition, the 3 y's condition, that's what we just saw, and the answer was roughly n over 2. But now I'm going to impose a 4 y's condition, so all 4 y's intersections have to have even size. And let's see what the largest such family is when I add that additional condition. So a construction is to have your ground set be the edges of the complete graph. And here we need n to be even. And now I'm going to define a family where each set is the collection of edges that contain a given vertex. Okay, so let's take a look at this family. The sizes of the sets from the family is going to be n minus 1 because there are exactly n minus 1 edges that contain a given vertex. So as long as n's even, this is going to satisfy that first condition. The pairwise intersection, this is going to consist of all edges in the complete graph that contain both the vertex I and the vertex j, and there is only one such edge. So the pairwise intersection is also going to have size 1, which is odd. Now the three-wise intersection, what does this say? It says all edges in the complete graph that contain the vertex I, j, and l. Well, I can't have such a edge, so that intersection is going to be 0. And similarly, the four-wise intersections are going to be empty. Okay, so this is a construction where the number of sets in my construction is n, and it looks, roughly speaking, like the square root of 2 times the ground set. So that's a construction, and it turns out that that is essentially best possible. So what I can do is I can consider all pairwise intersections from the family. So I have a family that satisfies that intersection pattern, and I consider all pairwise intersections. Now, the pairwise intersections are going to have an odd number of elements. So each set in this new family has an odd number of elements. What's maybe a bit more subtle is when I do all these pairwise intersections, I get a different odd size set each time. Essentially what's going on is if you look at these conditions, if you had some sort of collision, you'd eventually violate one of the intersection sizes. So it's a bit more detailed to write it down, but it turns out we're going to get a different odd size set each time. And moreover, if I take a pairwise intersection from this new family, it's going to correspond to either a three-wise intersection when you have something like F1 intersect F2 with F1 and F3. That would be a three-wise, and those are going to be even. Or if you have like F1 intersect F2 with F3 and F4, that is still going to be even. So no matter how you do the pairwise intersections from here, you're going to get something that is even. Okay, so what does that mean? It means this new family is going to satisfy oddtown rules. So the sets have odd sizes, and the pairwise intersections are going to be even. So that means the size of this new family is at most the size of the ground set. And if you carefully do the numerics, that means the size of your original family is something like root 2n. Okay, so the story is, as you add this additional condition, it's going to drop from something like n over 2 to the square root of 2n. Okay, so just to summarize the results again, we have 4 vectors here where there is a construction that's even close to linear size in the ground set. And then all these vectors here are going to be much smaller. Turns out that those are going to be the only 4 such vectors that are going to have a construction that's anywhere near linear size. Okay, so the 4 vectors that you can get anywhere close to much larger than the square root of n are going to be strong eventown, strong oddtown, alternating oddtown, and what I call delayed alternating oddtown, because you sort of have 2 zeros and then you alternate between zeros and ones. Okay, so we showed that there are only those vectors that are going to have a linear size construction. And if you're not that vector or its dual, the largest such family could have is some constant times the square root of n. Okay, and we have a similar conjecture where there's only going to be so many families that are going to have, so many vectors that are going to have anywhere that's close to some constant times the square root. So you can conjecture that for any k, there's an absolute constant, so that for any k, there's at most k vectors that have any construction that looks like a constant times root n. Okay. The last thing I wanted to talk about is this problem, but now with mod 3. So we had some conditions on the sets and pairwise intersections and 3-wise intersections, mod 2, and you can ask the same questions, mod 3. So a set family is going to satisfy 0, 0 star intersection pattern if the sizes of the sets are 0 mod 3, sizes of the pairwise intersections are 0 mod 3, and now the star condition says that it's non-zero mod 3. Okay. So this is a new problem, mod 3, and what we're trying to do, just like the other problems, is find the largest such family. Okay. So this is a problem that is open. I don't think we're going to solve it by the time we post it on archive. So it should be open. I hope someone can solve it. So why is it hard? One reason it's hard is, unlike in the mod 2 case, there's no duality mod 3. So the star 0 problem, where the sets have size non-zero mod 3 and the pairwise intersections have size 0 mod 3, sometimes it's called mod 3 oddtown. The answer there is n. And you can take the singletons all the same. Okay, so that's the star 0 problem. The 0 star problem is a particular case of the Deza-Frankel-Sinke result. And there, the upper bound is something that's quadratic in n. And in fact, you can actually take the 3 uniform star, and the 3 uniform star is going to have sets that are size 3, which is 0 mod 3. And the pairwise intersections have to be size 1 or 2. And that will give you a lower bound of n minus 1 choose 2. So unlike in the mod 2 case, there's no duality. Okay, so the construction for our problem is similar to the tale of 2 cities. So what do you have in your first city? You just have the sets consisting of all but one guy. And then your second city is going to consist of a graph perfect matching. So you have roughly 6k, maybe 6k minus 3, no, 6k minus 2 vertices in the second city. And each of your sets throws away a unique guy from the first city and adds a pair from the second city. So the sizes of the sets are going to be 3k minus 2 from the first city, and then there's going to be a unique pair from the second city. So that will be 3k, which is 0 mod 3. The pairwise intersections get no contribution from the second city because these edges are a graph perfect matching. And then you're going to throw away 2 elements from the first city. So you end up with 3k minus 3, which is 0 mod 3. And now the pair 3-wise intersections, what happens is you end up throwing away 3 elements from the first city. So why? Okay, so what does this give? This gives a bound of roughly n over 3. So this is a construction of 3k minus 1 sets, where the ground set is something like 9k minus 3. So it's roughly n over 3. The best upper bound we can do is essentially just translating the problem back into the Deza-Frankel-Sinky thing. So what do? You take all pairwise intersections with a given set, and now that's going to satisfy the 0 star intersection pattern. So therefore, you get the size of the new family, which is just the size of the family minus 1, looks like the sum of these binomial coefficients, which we have no control really over the sizes of the sets. So this could be something that's quadratic. So it's unclear if the answer is like n or n squared. And part of the difficulty is in the construction. This is always 2 mod 3. So if we want to fully utilize things, we need to have the 3-wise intersections be both 1 and 2 mod 3. So when we use this Deza-Frankel-Sinky for the upper bound, we're implicitly using that the 3-wise intersections are 1 and 2 mod 3, whereas our construction only has 2 mod 3. Okay, so that's all I want to say about that. Thank you for listening. And yeah, please let me know if you have questions.
Okay, let's thank our speaker. I guess people might unmute on Zoom and ask questions or put things on the chat. Does anyone in the room have questions for our speaker?
I guess I could ask a question. So the modulo 3 case is a bit difficult. But I want to ask, have you tried modulo 4 or modulo 5? Go up higher.
Yeah, so like for mod 5, some of the constructions, like the tale of 2 cities, the key is really like when you go from the sets to the pairwise intersections, you drop down 2. And then we go from pairwise to 3-wise, you drop down another 1. So a similar construction is going to work for many mod p values, just to get, as long as like n satisfies whatever condition mod p. We have not tried doing, all, 8 and 16 problems modulo p, but that would be interesting for future, research.
So you said you were talking at the very end about these problems where you have the star entries in your pattern and maybe not fully utilizing in your construction, that now there's multiple options for those congruence classes. Is it easier if instead of having the star, you specify that you want all these intersections to be 2 mod 3?
Yeah, so if you specify 2 mod 3, then it turns out the Deza-Frankel-Sinky theorem, it's going to give you an upper bound of n choose 1 plus 1.
Mm-hmm.
So that this theorem is a sum of binomial coefficients, n choose I, where I goes up to the number of allowed intersection sizes. So if you specify it's just going to be 002, then this construction is best possible, or it's at least very close to best possible.
Mhm.
It's somewhere between n/3 and like n or something like that.
Mhm.
Yeah.
Okay, well, I don't see any questions in the chat, and it seems like maybe we don't have any more questions here. So if that's the case, then let's thank Jason again for a great talk.
Yeah. Thank you guys for coming.
And I know that I've been substituting a lot lately, but when we meet again after Thanksgiving break, I think our regular organizer should be in town. So please, everybody, have a great break and stay tuned for an update on our next talk.